So now we are in 11.2, and we are looking at the ideal gas law. Really, the big piece of gas chemistry is always the ideal gas law. And what the ideal gas law, we already kind of alluded to it in the last couple sections, is taking our Boyle's law, again, our pressure-volume relationship. So this was our pressure is inversely proportional to volume. Charles' law, which said volume and temperature are proportional, they go up together. And Avogadro's law meaning moles and volume were proportional, and we were putting them together to make one rule or one law, so we didn't have to remember all of those. Again, what we did before is we wrote this combined gas law, right? P1, V1, N1, T1 equals P2, V2, N2, T2, and if you've watched all the episodes, you'll remember what I said is that we could really kind of get rid of that and have this equal to some constant R. That is what we are finally going to do. That if we have a pressure, volume, moles, and temperature of a gas, it's always going to solve for a constant R, and that is our ideal gas law. Now, typically we don't write it like that. How you'll generally see the ideal gas law is in this type of relation where we put PV equals nRT. P, again, is the pressure, volume, moles, temperature, and R is our gas constant. Now, what we're going to run into immediately trying to use PV equals nRT. So again, what this is going to allow us to do is to solve for any of these variables in a reaction. Now, one thing that people might have, easy enough moles is always moles. Temperature is pretty easy, that we always need it in Kelvin. Now, we have different units for pressure and for volume. And now, which ones are we going to use? Well, I'm going to tell you that typically volume is liters, almost always. Pressure, I like to use atmospheres, and most often we'll see things calculated in atmospheres. Now, I will warn you that that's actually not the SI unit for this calculation, and we do have to be careful of that, because if we have different units on our pressure, obviously our gas constant is going to come out in different units too. So the gas constant is dependent upon the units you use. So let's take note of this. Notice our unit of N, our moles are always calculated in moles. Our temperature is always calculated in Kelvin. Volume is always calculated in liters. Notice this one is in cubic meters because that is the standard SI unit of volume. But a cubic meter is equal to a liter, so that's easy enough. Our pressure is where it gets kind of spread apart here. Don't really use millimeters of mercury very often in our ideal gas law, but if we did, we'd get this numerical value of R. I will tell you that the one I'm going to remember, or I do remember, and the one that I use most often is this value of R, 0.0821. That's with our pressure in atmospheres. I like atmospheres. We use that most often. I will have you note that a lot of times, like it says here, our SI units might be in joules or liters times kilopascals. I don't really like that one to use it enough, but it is out there. If they have units that are in liters and kilopascals, do note that you might have to use that R. That there are different R's depending upon the units. This is the one I'm going to tell you to look at. And you know what? You can always use it because you can always convert your values into atmospheres and liters. So it should not ever be a problem. Notice where this calculation is. If we are solving for that R, pressure as 1 atmosphere, temperature at 273, 0 degrees, again, that's standard conditions. 1 mole of gas, again, 22.4 liters. You'll remember that from last chapter when we were looking at the molar volume of a gas. That is the volume 1 mole of any gas occupies at STP. Notice this is that R. Notice it's 0.082057884. Again, typically what we use is the 0.0821, and that's the one in your book kind of encourages you to use for R as well. Notice we do have to make sure that we have the right units so that things always do cancel out. If we don't have things in moles and Kelvin, atmosphere and liters, things will not cancel. We won't be able to use this equation. But since we have it, let's see if we can actually use it. So, notice number 2 should be pretty easy. What is the volume in liters of 0.1 grams of C2H2F2 vapor at 0.0982 atmospheres and 22.3 degrees Celsius? So first I'm going to write down my equation. PV equals nRT. There we go. What are we solving for? It says what is the volume? So let me rearrange this equation for volume. I'll just solve by P. I'll divide over there by P. So now my rewritten equation is volume is equal to nRT over P. Very good. Now maybe I can throw some numbers in. Pressure is right here. It's in atmospheres, which is good, so I can use the R I like. Again, you don't have to memorize this R, but this is the R that we'll use. The 0.0821. So I'm going to put that in. 0.0821. My temperature is what? Notice in Celsius, so be very careful. There's going to be a lot of converting in ideal gas laws. We'll have to convert that by adding 273.15 if we want to be very careful to make sure that we have a Kelvin value. So what would that be? 295.45. Put that in. So 295.45 is my temperature. My pressure was already in atmospheres, and since I'm using this R, that's just fine. 0.0928 atmospheres. Now the last thing I need is to substitute in my N. So this is my R, that's in. My temperature, I converted into Kelvin, put in. My pressure is already in atmospheres, so that works out. I can put that in. Now I just need to include my moles. Ooh, you'll notice they don't give me moles though. They give me grams. Ooh, so what do we do? One extra step. Now we could convert that grams into moles and then plug it in. Feel free to do that. Another relation that they want us to know is that our moles is our mass over our molar mass. That is essentially how we always solve for moles. So if we ever want to do the calculation-wise, it's always mass over molar mass. So I could do this. I could substitute that in for N in this position. So if I erase N, now I have mass over molar mass in my equation. So I can put them right into the equation. So what do we have for our mass? 0.1 gram. I'll put that on top, 0.1 gram. Now, if I'm using mass on top, now I have to find the molar mass of that gas to put on the bottom. Well, what is the molar mass of my gas? Well, I have to add it up, correct? So C2, so it's 2 times 12. It's H2, so 2 times approximately 2. I'm sorry, not 2 times 2. I'm thinking about 2 times 1, right, to give us the 2. And fluorine, which is 4 times 18.9, or I'm just going to write 19. So I'm going to estimate these a little bit, find that molar mass. So my estimated molar mass is 102 grams per mole. Okay, so now if we plug these in, again, it's kind of a lot. It gets to be a bit of a messy equation, especially if your handwriting is poor. But again, if you multiply across the top, divide by everything on the bottom, we can get an answer. So I'm gonna punch it in as we talk here. So it's 0.1 times 0.0821 times 295.45, and now I'm gonna hit divide by 102. That's the molar mass right here, and divide by the pressure, 0.0928. So there's nothing terribly difficult about these. It just involves plugging numbers into an equation, really, rearranging it occasionally, and now we get a volume. Okay, let's do another one, I suppose. 3 says, why must the units on PV, T, and N match up to those in the ideal gas law constant in solving these problems? Well, again, if they're not all in the right units, things don't cancel, and we'll get nonsensical numbers. We could set these up as we did our stoichiometry problems and show how all the units cancel. And actually, I probably should have done that on that calculation to show that the units in my gas constant were canceling. Because if we don't, again, the volume won't cancel. They won't make any sense. So let's do a calculation here instead. Number 4. What is the molar mass of a 1.25 gram sample of a gas that has a volume of 1 liter, pressure of 0.961, and temperature of 27? So again, this is always a good time in the podcast to go get another cup of coffee. No, it's actually a good time to pause it and try the calculation for yourself. Note, on this one, we'll have to substitute in the mass over the molar mass for N. And so maybe I'll do that first. But you can pause me at any time, try this problem, go back, see if you're setting it up right. So I have PV equals little m over big M times RT, and I'm solving for the molar mass, so I'm solving for that big M. So what I'm going to do is flip things around here. I want the M on top, so I'm going to multiply this side by M on the top because it's on the bottom here. Put M on the top over here. Do the same thing, so I have MPV equals MRT. This is where it's handy if you have some decent algebra skills. Now I'm going to divide this side by PV. and PV. Then you don't have to go through a long derivation. You can kind of just flip it and see how everything works. That is my new equation. Molar mass equals mass times R times T over PV. My mass, if I go back up, was in grams, 125 grams. Molar mass equals 1.25 grams. R is 0.0821. I'm not going to write it in now. I'll write it in. Notice I even put on the units for you so we can look at how everything is going to cancel out. Okay. Times my temperature. Again, my temperature was in Celsius, correct? So it's 27 degrees plus 273. 273.15 plus 27 degrees. So what is it? 300 degrees. 300.15 degrees Kelvin. 300.15 degrees Kelvin all over my pressure, which was already in atmospheres, thankfully. 0.961. One less piece of conversion that I have to do. And lastly, my volume. Let's go check what units my volume was in. Liters. Nice, and it's 1. Oh, that makes everything easy. So notice we just have to plug things in with the correct units. Now, I'm going to show you why we need the correct units. Because notice what our units on our constant are. Liters times atmospheres. Well, notice we have atmospheres and liters on the bottom, so those will cancel. Notice our Kelvin cancels with our Kelvin. Now, what units are left? Grams, and then over moles. So moles is on the bottom. Well, grams per mole, is that what I want? Well, of course that's what I want, because that's what our molar mass is calculated in ours is grams per mole. So my units do still cancel. So it's important to see that. Sometimes we get very carried away with just plugging numbers into calculations and getting an answer and not showing it the right. If we also put our units on, we'll know that our numbers are coming out correctly as well. So if we do this calculation, what we'll find we get is 32 grams per mole. Ooh, now what element could this be that has a molar mass? What's a gas that would have a molar mass of 32 grams per mole? That would be a good test question. This one's kind of jumping out at me, that 32 grams per mole. I've seen that before somewhere. I think oxygen has a molar mass of 32 grams per mole, if I'm not mistaken. Each oxygen is 16 times 2. There we go. So we can solve this if we know the mass of the gas, we know the temperature, pressure, and volume of the gas, we can identify what the gas is. That is kind of a cool problem.